Hi, I'm Dr. O. Today I would like to share with you a practical example of reinforced concrete beam design. If you have any questions on this video, you may reach me through this email. These are the two references used in the content of this video. Here, a design for reinforced concrete beam in grid line 1A, A to D is shown. Design inputs are the sectional properties, material parameters, and the actions. This video only shows the practical solution to shear design accordance to Eurocode 2, which is also the ultimate limit state design. This is the design procedure for the shear design. This is the shear force diagram for the problem. In this case, we need to provide shear design for support A and support B. Now we can start on the shear design. The shear design is accordance to clause 6.2.3 or the design procedure of floor that shown earlier. We will start with determining the concrete strut capacity, VRD max. At theta equal to 22 degree and theta equal to 45 degree. The VRD max can be obtained from these equations. In these equations, we need the BW, which is the width of the web, effective depth D, characteristic strength of the concrete FCK, and the theta. In the shear design, the theta shall be within 22 degree to 45 degree, and it shall not be more than 45 degree. VED is the applied shear force that we obtained through structure analysis, and for support A and D is 121 kilonewton. We will compare the VED with the VRD max. In this case, the VED is 121 kilonewton is less than the VRD max at 22 degree. Therefore, angle 22 degree will be used. The shear link can be designed using this equation. ASW divided by S ratio will be obtained. So in this equation, we need to input VED, which is the applied shear force, FYK, which is the characteristic strength of the link, and D is the effective depth, and the theta here will be 22 degree. Now we have obtained the ASW over S ratio. We need to determine one of these, either ASW or S. In this case, we are going to try length of 6 mm diameter. We will have the ASW available. For one number of H6, we have 28.3 mm squared, the cross-sectional area. In a sections, we will provide two links or two legs of links. Therefore, two numbers of H6, the cross-sectional area ASW will be 57 mm squared. From this ASW over S relations, by putting the ASW 57 mm squared, we can obtain the spacing S. And the spacing S shall be checked against clause 9.2.2 part 6, which limit the spacing of the link to 0.75 D. In this case, it's 326 mm. In no case, the shear link to be provided with a spacing more than 226 mm. So now, H6 175 mm center to center is suggested or proposed for support A and D. We can use the table ASV over SV to propose the link. So now we have obtained the ASV over S ratio, 0.289. Refer to this table and determine the value which is greater than the ASW over S required. Maybe you will ask how to determine the ASV over SP ratio. So here I show you the calculation. So for example, if I want to have a syrup diameter of 8 mm with a spacing of 100 mm, this is a calculation. The ASV over SP. The ASV is a cross-sectional area. Remember, we have two legs in a section. Therefore, pi d squared over 4 multiply 2. And we divide by the spacing SP. In this case, we want to know the spacing of 100 mm. So once we have this pi multiply diameter of 8 squared over 4 multiplied by 2 legs divided by 100 mm spacing, we can obtain a 1.006. Now we want to try to provide H6, which is not inside this table. So we can perform the calculation again using this equation ASV over SV. So pi d, the d will be 6 mm. Squared over 4 multiply 2 legs, divide, then we need to propose the value of the spacing. Let's say 175 spacing. So we will get 0.323 for ASV over SP. And the value is greater than the required. So this is satisfactory. The shear design in support A is applicable to support B and C. Shear force is commonly maximum at the support. If you can see the shear force diagram here. And it will be reducing when it is away from the support and 0 near midspan. It is not necessarily for us to provide the shear link throughout. Here I show you how to determine the minimum or nominal link. So nominal link or minimum links will be provided in this shaded area. So minimum links can be obtained through these equations. These equations will require the FCK, BW, and FYK. FCK and FYK are the characteristic strength for the concrete and the link respectively. BW will be the width of the web. So once you have obtained the ASW over S ratio, we will use the method that explained earlier to propose the link. So here in this case, minimum or nominal link is provided H6 300 center to center spacing. You need to remember to check this spacing against the limiting value in clause 2.9.2.2 part 6. The shear resistance of the minimum links for H6 300 center to center can be determined using this equation. The ASW over S ratio will be based on the provided link. The D is the effective depth. FYK will be the characteristic strength for the link, and the theta will be 22 degrees. So now we determined the shear resistance of this link H6 300 center to center is 79 kilonewton. In this shear force diagram, I drawn the position of 79 kilonewton. So it can be seen that the shear link is only provided at the distance or spacing X1 location x1, x2, and x3. And the remaining distance or locations, which is shaded in colors, we provide the minimum links. The x1, x2, and x3 can be determined using the interpolation for the geometry, the triangle geometry. Here I would like to show you the detailing for the link. The design output from the shear link and nominal link. The shear link is H675 at support A, H625 at left support B, and H650 at right support B. And the nominal link is H6300. If you can see from the elevation of the beam 1A, A to D, the links are detailed in such. This is the shear link, nominal link, and shear link for the right and left support B. There is another alternative to write the links detail. You can write H675 in bracket the distance or the length provided, the positions provided, x1, 1250 mm. Then the contractor will base on these details to provide the link of H675 with a distance of 1250 mm. But if you want to provide the details written in this page, you need to determine the numbers of links to be provided. So how to determine how many links to be provided for the shear link? For example, in support A. So you need to divide the x1 with the spacings that you provided, 175. 1250 divided by 175, you shall be able to get 7 or 8 number of links. Therefore, you write here 7 H675, center to center. In this shear design, it is necessary to allow additional longitudinal tension reinforcement that caused by longitudinal tensile force, the delta FTD, which is due to the horizontal component required to balance the compressive force in the inclined concrete strut. So additional tensile force shall be less than the MED max over Z. Then the additional longitudinal reinforcement as required star can be obtained from this equation. So now you have obtained the AS required, the additional longitudinal reinforcement. You need to add to the AS that required in your flexural design. So here are the AS required for the mid-span tensional reinforcement 5H20. So when provided near the support, so we allocated 30% of the AS required according to the guideline. So these 30% of AS required need to plus the additional longitudinal reinforcement that you have calculated. In this case, you obtained a 669 mm squared. So you need to make sure that the AS provided 3H20 is greater than 669 mm squared. This is the design procedure for determining the sufficient transverse steel in flange. This is necessary to check the possibility of failure by excessive compressive stresses in the struts and to provide sufficient steel to prevent the tensile failure in the ties. This is a sample of the calculation. Now I end my video on shear design for RC beam. See you in my next video.